In this part of the video, we'll be talking about the combustion time. As I told you earlier, we have three T's. Give you a second to remember them. Time, which is what we're talking about now, temperature, and turbulence. So we covered the temperature when we were talking about the flame temperature. Now we will be covering the time. So the combustion time for small flames are quite short, and for larger flames, they are not really longer. So if we have a very small thing, we have small time. If we have larger thing, we have longer time, and that makes a lot of sense. So let's, in the next slide, let's talk about three examples. One of them is the gas stove, auto engine, and large coal-fired boiler. They do have different magnitudes, so you can get a little bit of the idea. So in gas stove, the flames stand still while the gas premix air pass through them and oxygen diffuses in the form the air and complete combustion. So basically, the cylinder that you put at home is just the fuel. It does not really have any air. So where is the air coming? The air is coming in the line and it premixes inside the stove itself, and it premixes with the fuel to burn really where you have the flame, where you put your pot for cooking. The gas velocity is comparable to laminar flame speed, and we talked about what is laminar and turbulent. Laminar meaning that it does not intersect, it goes in straight lines, which means that the speed of the flame propagates into a fuel-air mixture that has no turbulence, which for methane is about 1 feet per second. The thickness of the flame is about 1/16 of an inch. That is a very, very small. The inch is 2.54 centimeters. So 1/16 is a really small thickness. So the combustion time is T is equal to L over V, where L is the distance and V is the speed. So it is 0.005 feet over the speed, which is 1 feet per second. This gives you a 0.005 second, which is 5 milliseconds. This is the time it takes for burning on your stove, for having this flame. Let's look here at an auto engine, and let's write here that the T was 5 milliseconds. Next is the auto engine. In the automobile engine at 2000 RPM, the time for one revolution is about 0.03 seconds. The combustion takes place in perhaps 1/12 of this time. So, however, the estimated time for combustion would be 0.0025 seconds, which is 2.5 milliseconds. Here, the distance traveled by the flame is about 2 inches. Here it was, the distance was 1/16. Here, the distance of an inch. Here, the distance is 2 inches. So that the flame speed is 20.3 meter per second. This speed is reasonable for premixed flame, but would not be plausible for a diffusion flame. Finally, the large installation of the large coal-fired fire boiler. This is a typical one that we use to generate electricity. For example, in a city like Al Ain, in a typical 500 megawatt coal-fired power plant using pulverized coal, the gas flow through the system is about 1.2 m standard feet cube per minute, which is equivalent to 5.3 m actual feet cube per minute at the firebox outlet temperature of 1800 Fahrenheit. So what is the difference between standard and actual? I'll give you a second to think about it. The difference is in the other things that come with the gas. So standard airflow is actually estimated at normal operating conditions or standard operating condition, which is room temperature, atmospheric pressure, and so on. However, when we talk about combustion, we talk about a very large change in temperature. So what the flow rate, which is actually changing based on the temperature, will be different. And in this case, we're talking about the actual flow rate. So let's say that PV is equal to nRT, which is always true. So in standard conditions, we'll have P1 V1 is equal to N1 R, which is a constant, T1. After we increase the temperature, pressure will change. So we can write P2 V2. The also volume will change. However, the number of moles, N, will not change because that's the same mass that will be inside. So N1 is equal to N2. So we can just write it as N in both of them, RT2. Having this together, we can say that N is the same. So P1 V1 over T1 will be equal to P2 V2 over T2. And based on the V's, we can estimate what is the actual flow rate. So if I can give you the standard foot cube per minute, which is called also SFCM, so standard feet cube per minute, you can calculate the ACFM, which is the actual feet cube per minute. So here we have, this one is called SCFM, standard cubic foot per minute. And the other one is called ACFM, which is the actual cubic foot per minute. And based on this relationship, P1 V1 over T1 equal P2 V2 over T2, you can actually convert between both flow rates. However, let's say now that this is what we are given, 1.2 million standard cubic foot per minute, and also equivalent to 5.3 million actual cubic foot per minute. And here are the dimensions of our firebox, which is 46 feet times 46 feet times 165 feet high. So the velocity will be Q over A, which finally is 13 meters per second. The time it takes to go up all 165 foot is 4 seconds. This value somewhat overstates the combustion time because much of the gas admitted above the bottom of the furnace, and because the value is based on the outlet temperature. And I'll explain that here in a second in the next slide, just to have some space to draw it for you. So let's assume that this is where the combustion happens. So flame is right there. Now the gas is going here and it's being collected right there. So the temperature, if you're looking at the temperature, it's, use the red color. This is really, really hot, 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 hot. And here it's hot. Here, 3 T's. Here it's 2 T's. And here it's just 1 T. So when we are saying that we're calculating the actual we are calculating it based on this temperature, which is not really fair for the time, because we have a gradient of temperature as we talked about it earlier. Additionally, the gas does not really travel the whole length of the boiler. However, it actually travels only from here to here, which is less than the length. So that's also overstates the time it takes for combustion. So we actually do have smaller time for combustion. In this table, we can see estimated peak temperature and combustion times in various kinds of burners. So we can see the candle. The candle, they go from 1900 to 2000 Fahrenheit, and the combustion time is 0.005 to 0.01 seconds. Kitchen stove, 0.005. propane torch 0.001 furnace that you can use for mid-size industrial furnace, 1 to 2 seconds. Large coal fire furnace, 2 to 4. Oxyacetylene torch, 0.001. Automobile engine, 0.0025, and so on and so forth. So in the next video, we'll be talking about the volume and the composition of combustion products